Hello, my name's Claire Whittam from the Atmospheric Dispersion and Air Quality team in the Met Office. In this talk, I'm going to give you a brief overview of the name dispersion model and highlight some of the aspects that you're going to cover in more detail in other parts of the course. So the name model was originally developed by the Met Office following the Chernobyl nuclear accident in the 1980s, which revealed the need to be able to predict the dispersion and transport of material over scales of about the size of Europe from such an accident. And lots of other centres developed models at the same time. So the acronym NAME originally stood for the Nuclear Accident Model. But since then, the functionality and the applications of NAME have developed and expanded considerably. And so we now use the NAME acronym to stand for the Numerical Atmospheric Dispersion Modelling Environment. And you can see that we have this nice branding at the bottom here. So what is NAME? What is the NAME model? So its use is for predicting the atmospheric transport of airborne pollutants, and that can be things like smoke, atmospheric pollution from transport, but also volcanic ash, and increasingly things like animal diseases and even midges. And we'll hear about that in other talks. So NAME is what's known as the Lagrangian particle model, and this was how it was originally developed. And so it models how particles or parcels of air move in the atmosphere. But as the model's been developed, it also now has what's known as an Eulerian model as a subcomponent, which works on a gridded basis. And again, there'll be more about this in later talks. Most of the time, NAME is driven by four-dimensional meteorological data, which is supplied by numerical weather prediction models, which means that it's enabled to be used entirely around the globe at different scales. And you can use it at very small scales, from sort of hundreds of metres to a kilometre, up to around the whole globe and hemispheric transport. And we've seen that in examples of volcanic ash plumes, for example. It's very flexible and it can be used at a whole range of time frames as well. So depending on the meteorological data you have available to you, you might be interested in very close to source impacts that occur over maybe a few minutes. Or you might be more interested in a climatological study looking at where material has gone or potentially has come from, if you want to run in a backwards style mode for many years. The flexibility of NAME means that it can be used to predict a whole range of parameters that you might be interested in, depending on your pollutant, from air concentrations at the surface, through layers in the atmosphere, as well as surface deposition, through wet and dry deposition, and a number of other things that might be important. So for radioactivity, for example, you might not be interested in the decay rates and the activity associated with it. NAME can be applied to a wide range of applications now, of which some are highlighted in this graphic. I've mentioned volcanoes, I've mentioned obviously Chernobyl and radiological incidents, but other things such as biomass burning. We can look at dust storms, air quality. NAME contains a chemistry model that we're increasingly looking at for air quality forecasting, looking at greenhouse gases, and being used to not only work out where things are going to, but also where things may have come from. And there'll be lots more detail on these applications in the talk on dispersion applications. So how does the modelling process work? This is a very simple graphic, and you can apply this to either using the model in a forecast mode or potentially the work that you might be interested to do. And as I've mentioned, one of the fundamental inputs into any dispersion model and into NAME is weather data. And so here at the Met Office, we run our own numerical weather prediction model. So this is what gives us the forecast every day. But that's based on hundreds of thousands of weather observations that are taken around the globe every second of every day to inform what that initial state of the atmosphere is. And as well as having forecast metadata, we keep an archive of meteorological data for running NAME on, and NAME's also able to run on other types of metadata, which I'll get to in a few more slides' time. The other important source of information for running NAME is actually information on the source itself. So what is being emitted, how much of it is there, where is it in the atmosphere? And those are a couple of key parameters to feed into the model. The model then runs, and you as a scientist or one of our operational meteorologists can then use that model output combined with other information they might have about an event or an incident, so observations, whether that's satellite, potentially measurements from a tall tower, other sources of observations and monitoring data, to do your analysis and to create whatever products or graphics or data that you're interested in. One of the key things with all models actually is that the outputs are only as good as the information you're feeding into them. So if you set up the model incorrectly or you're giving it poor input information to run on, you're likely to get unhelpful or potentially incorrect output. Often I hear people talk about the model being wrong, but in most of those cases it's because some of the input information that's been given to it has been incorrect or highly uncertain. So it's very important that we set up our models correctly and we understand how the uncertainty feeds through and where some of the sources of error might be in the results that we get. So I'm just going to highlight 4 areas where the uncertainty can exist in our simulations, and these are going to be picked up in more detail in some of the future talks. So I'm going to talk briefly about the model itself and the model parameterizations. I'm going to go back and just explain a little bit more about metadata, talk about defining the source, and also briefly touch on the importance of making sure you're asking for the right output. So first off, the model itself and model parameterizations. And what do I mean by parameterizations? Well, these are really how physical processes in the atmosphere are represented in the model. So some of the meteorology and the weather is coming through from the metadata, but there's a lot of processes that aren't captured in that and that the model needs to be implementing itself. So that's things like, how is my pollutant actually being dispersed within the atmosphere? What happens to it when it's then in the atmosphere? How does it interact with cloud and rain to be deposited out? Is it being chemically converted, or is it radioactively decaying, for example? What happens when it reaches the surface? And these are all things that within the model have to be captured by what we call parameterizations. And we're constantly developing those as more information and often more observations become available. And so this is true for all dispersion models, not just NAME, and different dispersion models will treat some of these processes in slightly different ways. And there's going to be a lot more information on this on the talk on NAME core science. The second source of uncertainty in any of our simulations, and this is both historically and in the forecast, is the meteorological data that we're using. So I've mentioned numerical weather prediction, and this is really the term used to apply to these large global and regional weather forecast models that a lot of national meteorological centres are running. And a large part of the dispersion model skill is actually due to the input meteorology. So if your input meteorology is wrong, or for example, it has a high pressure system in the wrong place, or it has the timing of a frontal system coming through slightly wrong, you can potentially get quite large errors in the positioning of your plume and your dispersion. Increasingly, the quality of NWP data from all global centres is improving massively, and so the quality of metadata today is much better than the quality of the data that we had 10 years ago, and large part of this is due to increased observations from satellites, but also increases in the physics that are going into these models. Within the Met Office, generally we get our metadata from our NWP model, which is called the Unified Model, or the UM for short, and these are acronyms you might see during the rest of the course. And it's the UM that provides the UK's national weather forecast that you'll see on sites like the Met Office website, our app, and other locations. And we have a variety of different flavours of the Unified Model, which come in different resolutions and cover different areas, and I've got a graphic on the next page. So here in the Met Office, for most of our operational purposes, we use output from the UM, but we've also developed NAME so it can run on other sources of NWP. So the European Centre for Medium Range Weather Forecasting, or ECMWF, they also produce daily weather forecasts and have what we call reanalysis archives. So this is historical data that they have gone back and reprocessed using modern techniques. And so NAME is able to run on both their forecast and their historical archives. Increasingly, the use of ensemble meteorology is being looked at for dispersion models. Ensembles are many realisations of how the weather may evolve based on minor perturbations in the initial state. And they've been used in weather forecasting for a long time. And there's some interesting questions about how we use them in dispersion models, and NAME's now able to run both on Met Office ensemble data and ECMWF ensemble data. And also, if you're interested in a very localised situation, or maybe you're trying to represent an idealised atmosphere, NAME's also able to run on what we would call point source observations. So often they would be from surface weather monitoring sites, but you may want an idealised distribution in the atmosphere as well. So what data is currently available for running NAME on? We have two main models that we use in the Met Office. And actually it's very important to understand what Met data you're using, because certain data is more appropriate than others depending on the application. So at the moment in the Met Office we have a global model, which, as it says, covers the entire globe, and that has a horizontal resolution of approximately 10 kilometres in the horizontal, and we take 59 vertical levels up through the atmosphere to about 30 kilometres at the moment, and that model updates 4 times a day. But we also have what we call the UKV model, which is a much higher resolution but limited area model, represented by somewhere in between the orange and blue squares on that map. And that has a horizontal resolution of 1.5 kilometres, and in the Met Office is run every hour. So if you're interested in a UK application, then you have much higher resolution data, which should be picking up features like topography in a much more detailed way. However, we also know that those limited area models, whilst they're higher resolution, they're very focused on improving surface representation of the meteorology. And so if you have a volcanic ash cloud, for example, where you're more interested in upper levels in the atmosphere, we tend to find that the global modelling actually does a better job in representing the dispersion at those levels. So thinking about the meteorological data that you're using is important when you start a piece of work. And as I've mentioned, observations are often used for impact assessment studies, etc. But they are only really relevant for the very local area to a site. And there'll be a lot more information on Met data, how you use Met data in NAME, how you set files up in the talk on Met data. So the third source of uncertainty is what I've called source information. And actually this is probably one of the critical sources of uncertainty in a lot of the work that we do with dispersion models, including NAME. So NAME has a lot of functionality when it comes to representing sources, and by sources I mean what is being emitted into the atmosphere, where is it, how much of it is there, how long is it being released for, and that sort of information. And so NAME has a lot of flexibility since it's been developed to a range of applications, and so you can have lots of contaminants potentially represented. So you may only be interested in one specific contaminant, but you can have any number of species in a simulation. NAME's able to represent both gases and also particulates, and it will treat those in different ways depending on how you set up the run. And increasingly we're developing functionality for those different species. So for particulates, for example, the user is able to specify whether you want a particular size distribution of the particles you're going to release into the model. You can specify the density, and also now we have schemes for specifying the shape. So typically and historically in dispersion models we've assumed that particulates are spherical, but we know that's not the case, particularly for species such as volcanic ash, and so we are now able to choose other shape parameters if we know that they're appropriate. I've also talked about NAME being able to do chemistry and radiological decay. And so when you choose your contaminants, you're also able to decide whether you want them to be stable or inert, or whether you want them to be decaying or reacting in some way. So once you've specified what it actually is you're interested in modelling, and sometimes you may not know, and so you can just use what we would call a tracer to work out the basic distribution of something. you need to also specify how much of it there is. And again, in some instances, particularly if something has just happened, in the Met Office, we often don't know how much there is, and so we have to make some assumptions or just work with what we would call a unit release. So that's just saying, well, we need to know where something may be going to. It doesn't actually matter at this point in time how much there is, so we'll just use 1 gram per second or 1 gram per hour, which is a quantity that can easily be scaled up. But you may have lots of information on your source, you may know exactly what it is, and so you're able to specify time-varying mass emission rates within the model, and they can also vary with height over time too. Or you might want to derive your source term from another model. Increasingly, there's a chain of models being used in a lot of studies, so you might have a source term model, you might have your dispersion model, then you might have some kind of impacts model. And the plot on the right hand side here, this is an example from volcanic eruptions, the volcanic ash, where looking at past eruptions and observations of the amount of material that's been deposited and observed, academics have been able to build up a relationship between the height of the eruption and the amount of material that's coming out. So this is a nice example of how we could derive a mass eruption rate from some other observation using an empirical relationship. And increasingly models are now being developed to represent that as well. So we may know our contaminant, we may or may not know our mass, but we also need to define how that's being released into the atmosphere. And as you can see from the picture on the right of the fire, the processes that happen in many releases are very complex and are often poorly understood, and we're not necessarily able to represent them in the model. So as the user of the model, there's a responsibility on ourselves to try to define the most appropriate source that we can. And NAME gives you considerable flexibility to choose different options to do that. So as the pictures at the bottom illustrate, you can just have a single point in time and space, you can have a line source, it might be a 2D plane, you can have some sort of volume, and you have the option for different shapes of volumes. Or if you know that you have a buoyant plume, but you just want to represent it quite simply, you can start to build up a series of sources to give you some sort of shape and structure. And these sources can be instantaneous in time, you can give them a time duration, or actually you can also make them vary in time. And so the source in some ways can be as complex as you're able to define it. And this is also one of the biggest sources of uncertainty in the model. So if we don't really understand what the source is, the model is only able to represent what we're asking it to do. And so sometimes starting with a very simplified source is a good way to understand what the basics of the transport and dispersion are going to be before we try to refine that source better. And obviously, if we don't know how much mass there is, our concentrations that we might be predicting are directly related to that mass. So there's a relationship there as well. For some species, you can also ask NAME to put in a met dependency. So for some of the work we do around animal diseases, certain impacts from the rain or from different types of temperature can affect how a source might get released, and the model is able to take account of that as well. So defining your source appropriately is very important, but it's also quite complicated, so it's just a note of caution. The fourth area of uncertainty is making sure you're asking for appropriate output. And again, this is a case of the user needing to be aware of what they're asking the model to do. The model won't flag up an "are you sure" question, it will just go ahead with what you've asked it to do. So NAME is able to produce a wide range of outputs actually, from what we might think of as fairly straightforward simple trajectories through to three-dimensional gridded outputs. You can ask for data on vertical slices or time slices, and you can also ask for information at specific locations, so you can get out a time series that you might be able to compare to observations on monitoring site data. But with all of these, because of the way a Lagrangian model works, it's important that you understand around making sure you're maximising your signal to noise. So if you only release very few model particles, your output's going to be very noisy, and the information that you get out might not be a really true reflection of what's happening in the atmosphere. So I'm not going to go into any more detail here, but there is information related to this on the talk on Name Core Science, which will talk a little bit about signal to noise and why that's important for a Lagrangian model. And then there'll be far more information on the different types of output that you can ask from Name and how to do that in the Name Outputs talk. So in summary, Name is a very flexible modelling tool, and it can be applied to a wide range of applications and situations. And hopefully you've seen at least a little bit of potential as to how you might be able to apply it to what you're interested in. I hope I've managed to give you a brief overview of some of the key components of dispersion modelling. What I've talked about for Name is applicable to all types of dispersion models, really. And I've highlighted a number of areas where we're going to go into a lot more detail over the rest of this course. And so if you have some questions coming out of my talk, hold on to those, and we'll hopefully be able to answer those in the Q&A sessions that are going to come up during the progression of the rest of this training course. Thank you for listening.